Hey class, we're going to be covering here 4.2, the mean value theorem, MVT, mean value theorem. This is a theorem that we pretty much, this topic right here can kind of stand by itself. We don't need it for what we're going to be doing as we move ahead, but it actually is used quite a bit in more advanced math. And we use it to actually help prove what's called the fundamental theorem of calculus. But here, we're just going to go through this, and then I'm going to give you some problems to look at, and that'll be the assignment for the class on Thursday that I won't be available to do the Zoom lesson for. So this is the video taking that place for that day. So let's talk about the mean value theorem. So before we get to the mean value theorem, we have to talk about another theorem called Rolle's theorem. And the good thing about Rolle's theorem, it's very visual. It's very, I think, easy to understand. So it says here, let f be a function such that these three conditions are true. So you've got some function sitting out there. First thing is it's continuous on some closed interval. All that means is that, on some closed interval, you can draw it without picking up your pencil. You don't have any breaks or jumps or anything like that in the function. Also, we need that we can differentiate the function on the inside of the interval. That means that the derivative exists everywhere inside that interval. That means we should have no corners, no cusps, no vertical asymptotes. The derivative exists everywhere in there. And the last condition is that we need that f of a equals f of b. That just means that the value of the function at the first endpoint is equal to the value of the function at the second endpoint. Those 2 points are at the same height. So let's take a look, first of all, about what this looks like. Here, we have an example of a function. It's defined on a closed interval. So it's defined between some value a and some value b. And we notice that the height of the function at the first endpoint is equal to the height at the second endpoint. So those 2 points are at equal levels. And I have a continuous function here. I draw it without picking up my pencil. There's no corners, no cusps. No breaks in the graph, right? Everything's nice and smooth. So the Rolle's theorem says this: if you were to look at connecting these two endpoints with a straight line, right? Connect those two with a straight line, the slope of that line is 0, right? Because it's flat. Rolle's theorem says somewhere on this function, I should have a tangent line that is also flat. So it looks like if we go right there to that point, the slope of the tangent line, right? The slope of the tangent line is equal to the slope of the line connecting the two endpoints. And I can give you another example. Let me clear this out. Let me give you a different function. So look at this function. It's continuous, right? Continuous on this closed interval. The two endpoints have the same height, and it's differentiable. No corners, no cusps, no jumps, nothing, no vertical tangents. So if I were to connect these two endpoints with a straight line, the slope would be 0. And I should be able to find somewhere on the curve where the slope of the tangent line is also 0. And in this example, there's actually 2 places where it happens, right? Here, we have a slope that's flat. Here, we have a slope that's flat. So Rolle's theorem is telling us, as long as it's, continuous, differentiable, the two endpoints are at the same height, which creates a flat line between them, we should have at least one, okay? It says that there's at least one point on the graph where the slope of the tangent line will also be equal to that slope here, which is 0. So that's the bottom part of this theorem. It says as long as these 3 conditions are met, then there must exist some number in the interval. So there has to be some number in here. In this case, that we're calling it, why am I not writing on that? Oh, I know why. This value c, there has to be some value c that when we come up here, the derivative at c will be equal to 0, which is the slope of the line connecting those two. Now, that's not the only c, right? There's another one here. We'll call this c2, we'll call this c1, where if we go here, the slope of the tangent line there at C2 is also 0, C1. So Rolle's theorem guarantees the existence of at least one. There exists a number C somewhere in there such that the derivative at that number is 0, but that's equal to the difference of the two endpoints. So that's Rolle's theorem. I have one more example to show you. Here's another example. This is just a straight line. And you can see here that if I look at this, right, the slope of the line connecting to these 2 points is 0. But if I go to any point in this, any point on this curve, the slope of the tangent line is 0. Rolle's theorem tells us there's at least one. Here, there's infinitely many, but Rolle's theorem at least guarantees one of them, or 1 point. Okay, that's Rolle's theorem. Most students are okay with that visually. So now let's move on to the actual mean value theorem. So the mean value theorem is a little different. All we're going to do, we're going to have the same three conditions, well, the same first two conditions. Okay, imagine there's a function that's continuous on a closed interval, so you can draw it without picking up your pencil, differentiable inside. Then that means there's no corners or cusp or anything. Then, okay, that third condition is gone. Okay, where we had to be equal at the ends. Okay, well, that's okay. What does this theorem say? It says then there must exist some number C in the interval such that, I don't know why that's so small, f prime of C, the derivative at C, come on, let me make that a little bigger. The derivative at that point is equal to this. Okay, what the heck is that? All right, well, let me show you with an example. Here's Rolle's theorem, right? Rolle's theorem guarantees us that if we connect these two endpoints together, the slope of that is 0, and that we should get a tangent line that's parallel to that. That's Rolle's theorem. Mean value theorem says we no longer have to have the condition that these two endpoints are the same height. So imagine if I just kind of rotated this like this. Okay, then what we're saying is that the slope of this line at some point, right, at some point C in here, the slope of the tangent line, f prime of C, that slope tangent line, should be equal to the slope of this dotted line. Now, the slope of that dotted line we could get by doing like a rise over run here. So the rise is the y coordinate of this point, which is f of b, that's the value of the function at b, minus the y coordinate at this point, which is f of a. And then divide that by the run. The run should be the difference of these two. So it should be that b take away that a, right? That's this b, this is b, and this is a. So b minus a. This right here is the slope of what we call the secant line connecting these 2 points. So mean value theorem is an extension of Rolle's theorem. Rolle's theorem, you have to be flat. Mean value theorem allows you to have different endpoints. And then you're no longer saying that there has to be somewhere in there where the derivative is 0. You're saying that there has to be somewhere in there where the derivative is parallel, right, to the secant line, the slope of the secant line here. That's the mean value theorem. Now, why do they call it the mean value theorem? Here's why this is referred to as the mean value theorem. The word mean here doesn't mean like angry and mad. It means it's the word mean is used in the sense of an average. The mean value of something is the average value of something. So let me bring something up here. I'll go into your folder here. I'll go right here. Okay, so for this, let's just say we have some, let's say this is time. Let's say it's measured in hours. Let's say this is distance measured in miles. Then let's say you start to take a trip, okay? So at time 0, you've gone nowhere. And let's say after 2 hours, you've gone 80 miles. So you're here. Now, how you got there kind of varies, right? You speed up, slow down. Everyone, can drive different ways. So there's different possible ways that you can get to that point like this. If we were to connect this point to this point, and find the slope of that, the slope of this would be the rise, which is here to here, that's 80. divide 80 miles, right? Divided by the run, which is here to here. This is 2 minus 0. This is 2 hours. And so what you get is 40 miles per hour. This is your average speed, right? Your average speed, or if you don't use that word, it's your mean speed. It is your average speed, your mean speed. What the mean value theorem says is that as long as this is a continuous function and we don't have any corners or cusp or any crazy jumps or anything like that, then there's some point in here, at some point within this trip, there's actually a few here, but somewhere around here, I don't know where yet, somewhere in here, excuse me, if I look at this point and I look at the slope of the tangent line, the slope of the tangent line there, the derivative at that point, let's call it C, the derivative at that point must be equal to this. It has to be. And the way you can think about it is like if you're taking a trip and you go 80 miles in 2 hours, your average speed is 40 miles per hour. The mean value theorem says that somewhere in that trip, guaranteed, somewhere in that trip, you had to be going 40 miles per hour at some point. It's impossible to average 40 miles an hour and never actually drive 40 miles an hour. So the mean value theorem guarantees us that somewhere in there, we had to go our average speed. And there's actually another point here, another one somewhere around here where the slope of the tangent line there is, parallel to this. And yeah, it looks like there might even be another one over here. Okay, the mean value theorem guarantees us at least one, but you could have multiple ones. And that's it. That's the mean value theorem. So let's see how we can use this to answer some questions. Constant function. Oh, last little definition here. If you ever have a function where the derivative is 0 all the time for every value in an interval, then the function has to be constant. So just think about a function where every time you go look at the function, you look at the slope of the tangent line at 0, then your function must remain constant the whole time. That's kind of a little ancillary thing here. Let's not get too much into that. Let's do a problem that involves mean value theorem. These problems kind of look different. I should say there's a variety of questions we can ask now, just using this theorem. The first questions are just going to be about us verifying that the mean value theorem is true. So let's do this. Let's say that we have a function. Let's let f of x be equal to x cubed minus 4x squared plus 1. And let's do this on the interval -1 to 1. All right. I want us to verify the mean value theorem. In other words, I want us to verify that there exists a number C in the inside of that interval such that when we look at the derivative at that point C, it should be equal to the slope of that secant line, f of b minus f of a over b minus a. So we've got some graph A, B, okay, and we need to show that there's some point C in here where the slope of this line will be equal to the slope of that line. This in here, right, that's the slope of this line, and this left side is the slope of our tangent line. Okay, that's what we're going to try and do. Let me bring up a graph. Let's take a look at this. Let's do x cubed minus 4x squared plus 1. Okay, there's the graph, and we're only looking at it between -1 and 1. There it is. Okay, hold on a second. Okay, so here's the function we're looking at, restricted on that interval. If we were to connect these two points here, the two endpoints, with a straight line, now of course the line would continue, but the slope of this line, we're trying to figure out where in here we have a tangent line on this curve that would be parallel to this. That's what we're trying to do visually. So how do we do this? Well, we're just going to work with this equation, this theorem. We're going to work with the left side and the right side and try and figure out when they're equal. So the left side should be easy because all we have to do is take the derivative of this function and plug c into it. So if I take the derivative of this, we get 3x squared minus 8x, right? And so if I plug c into that, I get 3c squared minus 8c, right? That's just the derivative with c inside of it. That must equal, now this side, I know what b is. B is the right endpoint, a is the left endpoint. So I want f of, let's see, b is 1, so f of 1 minus f of a, which is -1, over b, which is 1 minus -1. Careful, that's a double negative there. So we need to know when 3c squared minus 8c is equal to, all right, we got to plug 1 into this original function. So if we plug 1 in here, we should get 1, take away 4, it's -3, add 1, we should get -2, minus, now when we plug -1 in here, we get -1 minus 4, it's -5 plus 1 is -4. So we're subtracting -4, be careful there. I'm just verify this with the graph. When we plugged in 1, we got -2, plug in -1, we get -4. Is that what I had? 1 was -2. Yeah, 1, when we plugged in 1, we got -2. Then we subtract from that and we get what we get when we plug in -1, which is -4. And then all of that over 1 minus -1 is 1 plus 1, that's 2. So we get 3c squared minus 8c must equal, okay, the top is 2, right? -2 plus 4, it's 2, and then divide by 2, that's 1. And now we need to solve this equation. Just solve it for c. Well, it's quadratic, so we'll bring everything over to one side. And now, unfortunately, that doesn't factor. So I'm going to need to use quadratic formula. My solutions will be -b plus or minus the square root of b squared. Now b is -8, right? So b squared is 64 minus 4 times a is 3 times c is -1 all over 2 times a, which was 3. So I'm going to need my calculator here because I'm going to get decimal answer. 8 plus or minus square root 64 plus, I believe, yeah, plus 12 all over 6. So 8 plus or minus the square root of 76 all over 6. Get my calculator, I'm gonna get a decimal for that. We get 76 square root. So this is 8 plus or minus 8.7, I'm going to say 18 over 6. And now I have two different answers, one with the positive and one with the minus, or one with the plus, one with the minus. So I do 8 plus 8.718, divide that by 6. I get one answer of 2.786, and then the other one is 8, take away 8.8, no, 8.718 or 717, whatever, divided by 6. Oops, I messed that up. 8 minus 8.718. Get that answer, divide by 6. We get a decimal -0.119, something like that. Now, that's what we're saying, that's where it happens. That's where the slope of the tangent line should be parallel to the slope of that line connecting the two endpoints. Now, keep in mind, we're only looking in this interval between -1 and 1. And our answers, one of them is outside that interval. So we're going to throw this one away. And this is going to be our only one right there. So that is our answer. Okay, C is equal to -0.119. We're done. We're supposed to find the C where this happens. visually, let's go and take a look. If I were to plug in point, what was it? Negative 0.1. You know what? Let me plug in the point. Let's see. I'm going to call this f of x equals that, and then I wanted to plug in f of negative 0.119. F of negative 0.119. Okay, I'm going to plot that as a point. So let's let this be negative 0.119, f of negative 0.119. There it is. There's the point on the graph. So if we were to look at the slope of the tangent line, so if we connect these 2 points with a straight line, and then we look at the slope of the tangent line here, those lines should be parallel, which it looks kind of, yeah. I mean, if we would have got an answer over here, we'd be like, uh-oh, something's wrong. But that looks pretty believable. Now, we had another answer out here, didn't we? We had another answer at 2 point something, and I threw that away. Just notice something real quick. If I were to continue this graph on a little bit, okay. If I were to continue that graph on, it's going to be hard to show this. It's down here off the graph. I have to zoom out. Let's see if I can do this. I have to redraw this. So if I were to connect, was that one? It was these two connected, right? And then this right here goes from here to here. There was another point at 2 point something. Still not enough, but it's down here in the slope tangent line down there. But because that's not the interval we're looking in, we're going to throw that answer out. Okay, I hope that makes sense. All you're doing here is taking if you're verifying the mean value theorem, you're taking the function, taking its derivative, plugging in c. Then you're figuring out this, which is just purely algebra. Plug the endpoints in, subtract, divide by the difference of the endpoints, set these two equal, and solve the equation. Let's do another one. Let's do verify. So verify the mean value theorem for f of x equals 1 over the square root of x on the interval 1 to 4. All right, so 1 over the square root of x, that is not a continuous function everywhere. By the way, I didn't mention that. I should have mentioned that. This was a continuous function. It's a polynomial. That's why I didn't really mention that it was continuous. But the mean value theorem says we have to be continuous. So this one, we have a problem at 0, right? We can't plug 0 in. We can't plug negatives in. But the interval we're looking at only goes from 1 to 4. So if I plug numbers between 1 and 4 in there, I should be fine. So visually, what we've got here is we've got the function called g of x equals the square 1 over the square root of x. Okay, there's the graph. And we're only looking at this between 1 and 4. All right, so if we zoom in on this, if we were to connect the two endpoints, if we were to connect these two endpoints with a straight line, we're trying to figure out where in here we go to get a tangent line that would be parallel to that. Where is it? Okay, if we need to figure it out. All right, well, let's do it. So first thing I'm going to do is I'm going to write down the mean value theorem. It says that there exists some value c where the derivative at c equals f of b minus f of a over b minus a. And I'm just going to work left side down and the right side down. I need the derivative. So remember, this function is really x to the negative 1/2. So when I take its derivative, I get negative 1/2 x to the negative 3/2, which can be rewritten as negative 1 over 2 square roots of x cubed. That's one way we could write it. So I'm going to write that as negative 1 over 2 square roots, and I'm not going to use x because the theorem uses c, so c cubed. I need that to be equal to, all right, what is it equal to? F of b minus f of a over b minus a. Okay, so f of b, plug 4 into this. Plug 4 into that, you get 1 over the square root of 4, so that's 1 over 2. Minus, now plug f of a is 1, plug 1 into that, you get 1. All over 4, which is b, take away a, which is 1. So we get -1 over 2 square roots of c cubed equals, on the top -1/2, on the bottom 3. And now we need to solve for c. And this is not a quadratic anymore, it's something weird. So first thing I'm gonna do is I'm gonna multiply both sides by -1. That'll get rid of those negatives. Now let's just cross multiply, right? Let's multiply here and like that. So when we do that, we get a 3 on the left. We get a 3 on the left. On the right, we get a 2 root c cubed times the half that was there. And remember, we got rid of the negatives, so we can get now rid of the 2 and the half, those go away. So I get 3 is equal to the square root of c cubed. So now what I do is I square both sides of the equation. So 9 equals c cubed. And now I take the cube root on both sides. Cube root of 9 equals c. And that should be it. I'll do the cube root of 9 on my calculator. On my calculator, what I'm doing is I'm taking 9, I'm raising it to the 1 divided by 3 power. And I get about 2.08, something like that is approximately c. So that number does live inside this interval, and the mean value theorem guarantees that it will. So we'll get, well, it guarantees that at least one answer will live there. So that should be our c value. Going back to the picture, if I go out to 2.08 comma g of 2.08, that's the point. And if I do the tangent line, you know what, I can actually do the tangent line if you just give me a moment, if you'll bear with me. Y minus m equals g prime of m x minus, oh, I messed up, hold on. This is g of m. And then add a slider. There it is. Okay, so now here's the tangent line. Let me fix this. Let me only go between, what was it, between 1 and 4. Okay, so now you can see the tangent line there as I move along the curve, different places, right? There it is. I want to move it to where this is 2.08 right there. I don't know, looks pretty good to me. Let me connect these two with a straight line. That might be harder to do. I'll just draw it. Hopefully that'll be enough for you to be convinced we've done this. If we connect this point to this point with a straight line, we're saying these two lines are parallel. Looks good to me. All right, so that's really the way the mean value theorem works in terms of verifying it. Now let's see how we can use the mean value theorem to answer some other questions. So I have something else here for us to look at. Where is it? Let me see some of these. So for the homework, you're going to be asked to verify the mean value theorem for these functions. And then the ones that are interesting, I think, are these right here, these problems. So let's see here. All right, so let's look at number 17. Oh, I didn't get the instructions. The instructions are to, oops, show the equation has exactly one root. So show that this equation has exactly one root. Let's do 18. Okay, so if I look at this, x cubed plus e to the x equals 0, I need to prove to you that this only has one answer, one solution. Okay, one real solution. It's not, now notice it's not asking me what the solution is. It's just prove to me that there's only one answer. Okay, prove to me that there's only one answer. So what I'm going to do is I'm going to use two concepts here. The first concept is something called the intermediate value theorem that we studied a while back, which said that if we look at this left side right here as a function, so you have to look back in your notes at this. If we look at this as a function, to figure out when it's equal to 0 means we want to know where the x-intercepts are. So what we can do is we can ask ourselves, is this a continuous function? Well, x cubed is a polynomial, it's continuous. E to the x is an exponential function, it's continuous. And if you add two continuous functions, that's a continuous function. So yes, it's continuous. That means if I can show you that at any point it goes from a positive number to a negative number, then you know it goes through somewhere, it goes through the x-axis. So let me look at this for a second. If I plug in 0, I'm going to get 0, and then I'm going to get e to 0, it's going to be 1. So let me try this. If I plug in 0, I'm going to get 0 cubed plus e to the 0, that's going to be 1. Can I get a negative number? Let me try -1. What happens if I plug in -1? I plug in -1 and I cube it, right? So -1 cubed, and then plus e to the -1. This is the same as I already cubed the -1. So -1 plus 1 over e. But wait a minute, 1 over e, that's a small number. So if I do this on my calculator, -1 plus 1 divided by e, I get that this is -0.63. So look what's happened here between -1 and 1. So what I know about this graph is this: when I go to 0, right? When I go to 0, it spits out 1. So I know my graph does that. If I go to -1, I know that my graph spits out a negative number, so my graph has to be down here somewhere, which means it must pass through here. It has to, because it's continuous. Okay, so it went from a positive, or actually, because the numbers are backwards, it switched, right? It switches signs. Okay, that tells us, what does that tell us? We have at least one answer, at least one x-intercept. We need to show that it has exactly one. All right. See, we don't know. It could do something like this. It could go here and then through here a couple of times and then wind up here. We have no idea how many times it goes through the x-axis, just that it does at least once. I need to show it's only once. So the way I'm going to show it's only once is actually pretty clever. All I'm going to do is I'm going to look at the derivative. Okay, look at the derivative of this. The derivative of this function, take derivative of that, you get 3x squared plus the derivative e to the x is itself. Now, what's interesting about this function is that no matter what x I plug in, no matter what x I ever plug in, I can guarantee you that this right here is always a positive number, because x squared is going to be positive. I mean, at the worst, it could be 0, right? But then I'm going to add to that, now this e to the x, we know that no matter what you plug into e to the x, no matter what, it's always positive. And if we put those two together, it's always positive. And if I tell you that the derivative of something is positive, that should make you think, well, wait a minute, that means the function's going up, right? Because if the tangent line is always positive, the function's got to be increasing. So what we're saying is that when you draw this function, it always goes up. And if I have to get from this point to this point, and I always have to go up, then it would be impossible for me to go up and then come back down across through and go back up. That would be impossible. So it would have to, I don't know what it does, but it would have to go through and continue to increase and go up. So since f prime is positive, the function can't turn back, right? It can't turn around. So you only have one x-intercept. Boom, we're done. This is a weird type of problem because it's not like you're working out a bunch of math. You're just trying to show some things. So on these other ones, you do the same thing. You say, okay, I want to show it has exactly one root. First thing you want to do, make sure that, set it all equal to 0. Make sure that that's a continuous function. Use the intermediate value theorem to show 2 points where it changes signs. Then take a look at the derivative and show that the derivative is either always positive or negative. And if it's always positive, it has to go up, so it can't make any turns. And if it's always negative, it has to go down, it can't make any turns. So weird, right? Because this really had nothing to do with the mean value theorem, but it's in the section for mean value theorem. So see how it goes with that. Really, like I said, this is kind of a standalone section. We don't really need much of this moving ahead. Yeah, that's it. I think let me think. I got time-wise. I think that's all I'm going to do for this. It's a short lecture, not a big assignment, but it should give you something to think about, ponder before we meet again.